Second. All right, so it appears that we are indeed good to go. So good evening. And today we are going to be finding triangles, at least to begin with. That's what we are going to do. This is miniature number 10. And I have to confess that I haven't actually solved this opening question in the book, in the miniature, where we are challenged to find a triangle in this graph. And well, it's not visibly easy, and I should probably emphasize that we are not looking at triangles of the geometric kind. So let me see if I can emphasize that in some way. So for instance, this thing out here, that's not the sort of triangle that we are looking for. We are looking for a triangle which is formed by these endpoints here. So I want three of these vertices on the outer rim, so to speak, that have that are pairwise connected by edges. And here, for instance, this is somewhat promising because you have this edge and then you have this one going all the way, but I don't think you have the missing edge. So, so that's not quite a triangle, and this is not the kind of triangle that we are looking for. Okay, so basically we are given a collection of, points and lines that connect some pairs of these points, and we're looking for 3 points that are pairwise connected by these lines. And sometimes instead of points, I'll say vertices, and instead of lines, I'll say edges. What we are looking at is a graph, and we are trying to check if this graph has a triangle in it. If somebody has found a triangle, let me know. I like from all the squinting that I did, I couldn't find one quickly, but I do think that given that there are a large number of edges in this graph, I've only counted roughly. There are results which tell you that there are only so many edges that you can have while still avoiding triangles. And based on that, I'm tempted to conjecture that there is one, probably more than one even, but it's just such a tangly web of lines that maybe I'm just not seeing right, and I haven't been able to find one. And I've also, unfortunately, I didn't have the foresight to label these vertices. So if you found one, you will probably have to annotate it, and roughly that's probably how you can share your findings. But more generally, oh no, can you not hear me? I see. Okay, all right. I thought I was in mute. So Manu, maybe you have to check your volume settings or something like that. Yeah, I'm glad I didn't do I've kind of stopped doing the sound check, but all right, perfect. Thanks. Great. So yeah, so the question would be,
so is this a triangle?
Have you found one?
I don't know. I mean, let me see if we can annotate it.
Yeah, hopefully annotations are enabled.
I hopefully haven't. Is this a triangle?
All right. I think you would be right, actually.
Okay.
Oh, fantastic. Thank you. Yes, so I guess we have that edge there, and these edges cutting across. I am not being very respectful of the straightness of these edges, but great find. Okay, so that's indeed a triangle. So we know for sure that there is one. If I remember to, I'll probably try to make more explicit the result I was relying on by proxy to say that if you have a certain number of edges, then you're guaranteed to find a triangle. So we'll come back to that in a bit. But the question that we want to talk about is, well, how do we find these triangles algorithmically? So, all right, I'm probably going to clear. Okay, I didn't clear my annotations, so let me do that. Okay, all right. So, yes. So how do we find a triangle in general, procedurally? So we're going to rely on the so-called adjacency matrix of a graph. So the adjacency matrix of a graph that has n vertices is a n by n matrix, which basically captures the signature of what pairs of vertices are connected by edges. So for the graph that you see on the left, you can hopefully tally up, and I'm going to hope that there are no typos. But for instance, the green and the red vertices are connected. So the row and the column indexed by red and green have a 1. And it's symmetric because our lines are basically they don't carry any orientations. If they were oriented and if they had arrows pointing in one or both directions, then you can also capture that using a matrix like this, and the matrix will simply no longer be symmetric, and you need to have some convention of where do you place the ones, like which arrow direction corresponds to what row column indexing. But that's kind of not going to be super relevant for us, so I won't talk about that anymore. Just to make sure that we are on the same page with respect to the definition of an adjacency matrix, can maybe somebody just tell me which entry will change if I added that edge in? First of all, 2 of the entries would have to change because this is, like I said, it's a symmetric matrix. So every edge is represented by 2 ones in the matrix. So if I added that edge between the orange and the green vertex, I would have to update which 2 entries in the matrix. That would be 2, 3, and 3, 2. In the orange and the red vertices are the second and third rows. So we're going to have to flip those entries to a 1. So this is the matrix for this graph. If we dropped this edge, that's the edge between the purple and the blue vertices, then we would have to get rid of the ones that are sitting in the last 2 rows and columns. So these ones here would flip to 0. Okay. So is the matrix representation of a graph okay? All right, perfect. So, all right, then. So then we want to think about the square of this matrix. So what does the ijth entry in the square of this matrix capture? So let's think about, for instance, here, just written the matrix out twice to make it visually convenient. So the ith row and the jth column, what is the meaning of the number that comes out of multiplying the ith row and the jth column? In this case, we have the ith highlighted row is kind of representing the green vertex, and the jth highlighted column is representing the blue vertex. And remember that the ones in these rows and columns really are capturing the neighbors of these vertices. So for instance, if you look at the green row, that's triggered to 1 on the red and the orange columns. And this is to reflect that the green neighbor has the red and the orange fellows. The green vertex has the red and the orange vertices as neighbors. And similarly, the blue column has the red and the orange fellows again. So it's just a coincidence that in this case, the highlighted rows and columns happen to have the exact same set of vertices that they have edges with, or that they're adjacent to. But yes, as has been pointed out in the chat, edges number of, I would say the number of common neighbors is kind of the terminology I would use, or the shared neighbors. Edges which connect to 2 hops, also makes sense. Basically, you're looking at in how many ways can I get from I to j in 2 hops, if you're thinking of every edge as being a hop. And so I think that's pretty much what's come through in the chat. There's a comment about the degree of the vertices. So the degree is captured by, the degree is basically the number of edges going out of a vertex, or the number of vertices that your neighbors with. And again, if I use words that don't make sense, please let me know. But neighbors would simply be vertices that you have a direct connection with, that you have a direct edge to. So the degree is captured by the number of ones in a row or a column represented, that's representing a particular vertex. So for instance, the number of ones in the first row is 2, and that tells you that the degree of the red vertex is 2, and so on. But the ijth entry in the square of this adjacency matrix gives you the number of common neighbors between the vertices I and j that are being coded by the ith row and the jth column. So for those of you who prefer notation to pictures, this is straight from the miniature. They use A to denote the adjacency matrix. So the Aij entry is 1 precisely when I and j have an edge between them. So vertices are indexed ij and so on. And we're looking at A squared, and notice that the only terms that survive are those vertices which see both I and j. And that's why when you sum over all the entries, what you're really pulling out is vertices that see both I and j, the number of such vertices. So, okay, maybe this is a bit of a spoiler. If you look at A squared, how can you use the entries of A and A squared to detect a triangle? So if A squared ij is 1 or more, what does that mean? That means, well, I and j have at least one shared neighbor. So I, j, and that shared neighbor would form a triangle if what? If I and j have an edge between them, if I and j are themselves connected. Exactly. So for instance, here, the red and the orange vertices have the blue and the green vertices as common neighbors. And either of those common neighbors would basically witness a triangle if we had that edge between the red and the orange vertex, which we don't at the moment, but if we did, that would work out. So essentially, this just boils down to saying that we want to look for two indices such that the ijth entry is non-zero in both A and A squared. The fact that it's non-zero in A means that these are two vertices that already have an edge between them. You can think of that as the base of the triangle. And the fact that A squared ij is non-zero means that there's at least one other third vertex, which is such that it's adjacent to both I and j. So those three would come together and form your triangle. Is this all right? Does that make sense? All right, perfect. That's essentially the heart of the main point being made in this miniature. And so you can find triangles as fast as you can square matrices. So there is the question of, how fast can you multiply two matrices? And this is a very, very fundamental question in algorithms. And there are lots of people who have worked on this for a very long time. Yeah, so, okay, sorry, I'm just going to take a break to look at the question in the chat. Can we say that there are exactly 3 hops to reach back to the same point? Yeah, basically you're looking at, that would be one way to describe a cycle in general, and a triangle is a cycle of length 3. So if you can, if you can take a certain number of hops and come back where you started, and, well, okay, there's some complications in terms of terminology. There is terminology to distinguish between, did you revisit any other vertex, or did you only go through distinct vertices until you came back, and so on. So a simple cycle would be if you just came back and you only visited, and this was the first time that you're revisiting a vertex when you come back to where you started. But you could think of doing like an infinity loop where, okay, maybe that's not the right visual, but you could have done more cycly things on your way back, and so that would be an example of what would be called a closed walk. If you come back to where you started, but you do a bunch of things in between, and you may have revisited other vertices as you took your journey as well. So yeah, basically this notion would also capture the concept of a triangle, that you did 3 hops and you came back where you started. So in fact, it's probably a nice exercise to check that if instead of taking the square of the adjacency matrix, if you did A raised to k instead, then you capture the number of these longer walks between I and j, but they're no longer simple in the sense that these walks could be hopping around and revisiting the same vertices multiple times. So that's food for offline thought, I think, to think about what happens when you have more hops, but that's a perfectly valid way of putting it as well. So coming back to the sort of computation time, you can do this as fast as you can multiply matrices, and you can multiply. So if you just did, matrix multiplication as we imagine it, then you're essentially doing n operations for computing each of the n squared entries in the output matrix, because you're doing this kind of dot product, which is n additions or maybe n minus 1 additions. And you're repeating this for computing each of the entries in the product matrix. So that's overall n cubed time. And by being just a little bit clever, you can do better than n cubed. And by being very, very clever, you can go much better than n cubed. And this is, I think, a still active area of research. There are people who are still kind of in the race for improving the constant in the exponent of this matrix multiplication running time. And there have been developments that are even quite recent, but I'm very bad at remembering the exact numbers. So at some point I will update this with a reference, but the point is that we can do this faster than n cubed, which is nice. But this also takes us straight to the next miniature. Okay, I do have a prompt for, okay, what can we say about 4 cycles? So 4 cycles would just be, in the language of the comment in the chat, you take 4 hops to come back where you started. And in this image, for example, we do have a 4 cycle kind of between the red, green, blue, and orange vertices. What does the adjacency matrix tell us about 4 cycles? Okay, I don't remember if I phrased that question correctly. What I wanted to ask is, what does the square of the adjacency matrix tell us about 4 cycles? And not the adjacency matrix itself. So, useful way of thinking about a 4 cycle is that it's basically 2 vertices that have 2 common neighbors. So for instance, here, the red and the orange vertices have 2 common neighbors, or the blue and the green vertices have 2 common neighbors, whichever way you want to look at it. So whenever you have a 4 cycle, take the 2 non-adjacent vertices or the non-consecutive vertices. And then if you look at the other 2 vertices, they are going to have both of the other ones as common neighbors. Okay, so I guess I should distinguish between whether I'm looking for what is called an induced 4 cycle versus just a 4 cycle. So Jagdish is talking about INJ having an edge between them or not having an edge between them. So at this point, I don't really care about the so-called diagonals or the chords of this 4 cycle. I only want to know if there are 4 vertices, which are such that 4 vertices A, B, C, D, such that AB, BC, CD, and DA are all edges. There could potentially be other edges between these vertices or not. I'm not going to worry about that. I'm just looking for 4 vertices that have these edges going between them. Right. So Jayati is saying if there are 2 paths between 2 vertices, that will be 4 cycle. That will be a 4 cycle, exactly. So the number of common neighbors is at least 2. That's another way of putting it. So we look at the entries in A squared. And if we find one that is bigger than 1, then we are happy. Because that's basically saying that you have these 2 vertices that have at least 2 common neighbors. So you can take those 2 base vertices and the 2 common neighbors. And I don't know if there's maybe any edge cases that I'm neglecting, but you can, I think, basically use these 4 vertices to form your 4 cycle. And in fact, you can extend this to also even count the number of 4 cycles, because if you have, for example, an entry, the ijth entry of A squared being some k, that means I and j have k common neighbors. So you can pick any 2 of them to form a 4 cycle with ij. So you can do k choose 2 and sum these values of over all the upper triangular entries, because by symmetry, you would just be overcounting if you did both. And in fact, you'll still overcount a bit if you think about it. So you probably have to divide by 2 or something. But That's the basic idea. So the matrix A squared also gives you information about 4 cycles, and in fact, even helps you count them. But it turns out that you can directly compute 4 cycles faster than, in fact, you can do it in order n squared time. So you don't have to go through matrix multiplication. You can do something that's more direct, but that's a topic for another day. So I'm not going to go into algorithms for finding or detecting 4 cycles, but it's just interesting, and I think this is mentioned in the miniature as well. So it's interesting that the parity matters. So odd length cycles are generally harder to find than even length cycles somehow. So okay, so on that note, let's maybe start looking at the next miniature, where we are talking about matrix multiplication, and we are saying that, well, it's, there's a lot of interest in being able to multiply matrices quickly. We know that it can be done in n raised to 2 point something time. And let's say somebody comes to you and says that they have this proprietary algorithm, which is very valuable, so they won't tell you how it works. It's a black box, but you're welcome to use it. And it multiplies matrices lightning fast, okay? Better than anything that we know that has been published. And of course, you're keen on using it, but you don't believe this person. What if it's a snake oil salesman? So you want to be sure that this algorithm that's being sold to you actually works. So you want to develop your own sanity check algorithm, which basically tries to figure out if the matrix wizard is actually doing its job correctly. Yeah, so that's our goal. Our goal is to figure out if A times B is indeed equal to C or not. So is the setup clear as to what we want to do? We just want to come up with a validation algorithm. And of course, one way to validate matrix multiplication is to multiply the matrices ourselves. But we don't want to do that because the whole point is that we don't have all this time to multiply matrices. So we want to take advantage of this suspicious looking thing, but we want to do it without wasting a lot of time. So we want to quickly check if this algorithm is reliable, whether it works correctly or not. So we want to avoid multiplying the 2 matrices. So without multiplying A and B ourselves, can we check if the output of the matrix wizard is all right? Yeah, that's the question. Is the question clear? Awesome. So this is our goal. We want to develop this sanity check algorithm, and here's what we are going to do. It's going to be a randomized sanity check. So A and B are n by n matrices. You're going to generate a random vector X with entries in 0, 1. And I think I did not mention this, but A and B, we can assume are over rationals because that's mostly the real world setting that one is in, but most, I mean, this would go through for your favorite field. So we just for the sake of having something concrete, let's say that our matrices are over rationals. So we're going to generate a random vector X, which has entries 0, 1. It has n of these randomly generated entries. So the way to think about X is that it has n coordinates. For each coordinate, toss a coin. If it's heads, then you write 1. If it's tails, you write 0. And make sure to toss a fair coin every time. Now what we are going to do is apply C on X and apply B on X, and then apply A to the output of that. Okay. Now, if our matrix wizard was functional, if it always computed C as A times B, then what do we expect these values to turn out to be? The outcomes of CX and ABX. We expect them to be the same? Exactly. We expect them to be equal. So our algorithm is really simple. It says that, well, if they turn out to be equal, you give your matrix wizard a passing grade. Otherwise, you say, well, this is suspect. Something's definitely off. Okay. All right. So if the matrix wizard is accurate, then we will always pass. We'll always say that you did a great job, right? But on the other hand, if the matrix wizard is cheating, what can we say? Right. Okay, so Jayati is asking, can it be, okay, so this vector is randomized. So if C and A times B are indeed equal, no matter what your X is, these outputs will be the same, right? If the matrix wizard is genuinely multiplying A and B correctly, so if it's guaranteed that C is indeed A and B, then no matter what the randomness, because A times B is equal to C, Cx and ABX will be the same. Does that make sense? But I don't know if your question was pertaining to this, but yeah, okay, so my point is that we're looking at it from the perspective of, what is the truth? If the truth is that the matrix wizard is working, then our sanity check algorithm will always output yes. But okay, so we're still thinking about the case when the matrix wizard is accurate. So the point here is that X is arbitrary but fixed. I mean, although I said X is generated randomly, the point is that so we're making this huge assumption that C is equal to A times B. If that assumption holds, then for every X, Cx is equal to ABX, right? So in particular, for a randomly generated X also, it's equal. And also maybe let me just quickly highlight that Janki is talking about polynomial identity testing. I think, yeah, this is indeed in a very similar flavor. So JD, there will be situations where our test may not work, and maybe once we look at the flip side of the coin, hopefully this will become clearer.
Can I just add something here? I don't
Yes.
know, just in case it's not clear to her.
Right, please.
So I think all that's being said is that if AB equals C, then for all X, ABX equals CX. If it's not the case, if AB is not equal to C, there is an X where hopefully ABX is not equal to CX. And hopefully what we'll see is that it's not that there is an X, but likely there are many X's, or the density of X's is quite large. Does that make sense?
Sure, yeah, I got it a bit. I'll think about it.
Yeah, so this is the, okay.
Sure, thanks.
Yeah, perfect. I think we should leave that in for a bit as we go to the slide as well. Thank you. Thanks a lot, Vinay. So, all right. So if the matrix wizard is cheating and C is potentially not equal to A times B, maybe not all the time, but there are some failures, whatever. So let's say that we are in the situation where C is not equal to A times B. The question is, will our sanity check algorithm certainly catch it? Well, here I claim that we could have an issue. The sanity check algorithm may give a free pass to this algorithm in spite of C not being equal to A times B. So you might be fooled, but just like when I said, we're going to be fooled only half the time. So if the matrix wizard is cheating, our sanity check algorithm will still give it a pass with probability at most half. So when the sanity check algorithm outputs suspect, you can be absolutely sure that there was a problem because, well, that means that you actually have a witness. You have a X for which CX is not equal to ABX. So you know for sure that C was not equal to A times B, right? But on the other hand, if your sanity check algorithm gives a thumbs up, then it could be that this was a genuine algorithm and C equals A times B, but it could also be that C is not equal to A times B, but somehow we have generated a poor choice of X where ABX and CX happen to look the same. Okay, so all right, so the comment in the chat is that for all X, ABX and mu CX must be high. I don't know how exactly we're quantifying high, but yeah, it will give false positives, but not false negatives. When the sanity check algorithm complains, you can be very confident that there's definitely a problem. But if it says clean sheet, then you're still not sure. And here is an example of why, but I mean, I guess it's going to prompt this as a question, but in the interest of time, maybe let me just run through an example of the kind of issue that might arise. So for instance, here's A and B. A is, I think, the identity matrix, and B is something that is not the identity matrix. So the output is not the identity matrix. But if you look at all that B is doing is permuting the last two entries of X. So if the last two entries of X are identical, then the action of B on X will still give you just X, and A is the identity matrix. So A will act on that output and give you X. So suppose your matrix wizard took this pair of matrices A, B as input and decided to output the identity matrix, which is not A times B. A times B is B, which is not the identity matrix. But C says, the matrix wizard says, I'm going to output C, which is the identity matrix. Then notice that, well, our sanity check algorithm will say, well, this looks fine because ABX is X and INX is also X. So this is an example of a failure mode for the sanity check algorithm. Does this help? I mean, is this making sense? A valid example of when the sanity check goes wrong? All right, perfect. So moving on, we want to argue that these kinds of failures don't happen too often. In particular, they happen with probability at most half. So, well, let's think of this matrix, which is defined, which is D defined as C minus AB. And well, if C is equal to AB, that's the nice situation. That's when the matrix wizard did the right thing. So if if C is equal to AB, then D is all zeros, and here we have nothing to prove. Okay, but on the other hand, if D is a non-zero matrix, we want to say that, well, hopefully, we detected. So what do we want to say? I think I want to say that Y doesn't collapse and become the zero matrix too often. So when D acts on X, I want the outcome to be non-zero with probability at least half, or zero with probability at most half. Okay, that's what we want to show. Okay, so Y being zero is saying that CX and ABX are the same, and the sanity check algorithm will give you a false positive. We want that to happen with low probability. Or in other words, if D is non-zero, we want dy to also be non-zero. This is, I think, also what's there on the annotation, but just written in terms of matrix differences. So we are hoping that dy ends up being non-zero with probability at least half. Okay. And for this, actually, let me just skip ahead a little bit. Suppose this is our D matrix. And here, we know that D is non-zero. So let's hang on to some non-zero entry in D. Let me call that Dij. I know that D is non-zero, so there must be at least one. So let's just spotlight, our favorite non-zero entry in the matrix. Okay. And now let's look at the action of D on a random vector X. All right. The action of D on a random vector X gives us this vector Y, where the jth entry is, well, it's essentially the product of this row here, the highlighted row here, with the X size. Right, so I want to particularly highlight this product Dij Xij. Dij times Xj. We know that Xj was an independent and fair coin toss, right? So Xj is 0 with probability half and 1 with probability half, right? And remember, what I want to do is say that Y is non-zero with probability at least half, right? So now, if S, which is the sum of all the other DIKs with XKs, other than the jth entry, if that value S is non-zero, right, then even if xj is 0, I'm happy, right? Okay, so maybe this is not the cleanest way of bifurcating the cases. So let me just show you the way it is, the way it's most convenient to write this out. So if xj is equal to 1, then yj's value is dij plus s, whatever this remaining sum is. And if xj is 0, then its value is s. Is this fine? Is this claim about the value of yj based on whether xj is 0 or 1? That makes sense? Okay, good. Now, can it be that yj is 0 in both scenarios? For yj to be 0 in both scenarios, first of all, s has to be 0. But if s is 0, we know that dij is non-zero, right? So s cannot, for example, go and cancel the effect of dij, right? And if s is non-zero, then it's non-zero. We're already happy. And it's possible that s is non-zero and its value is minus dij. That's probably really unlikely, but never mind. I mean, the point is that if s is non-zero, we are already good on one of the coin tosses. If s is 0, then the other coin toss will save us. The other outcome on the coin toss will save us, right? So the claim is that whether xj turned out to be 0 or 1 in your random process, yj will be 0, will be non-zero in at least one of those scenarios, right? So it's going to be, and that depends on the value of s. If the value of s is 0, then when xj was 1, yj is definitely non-zero. And if s is non-zero, chances are that yj is 0 most of the time, except for this one weird corner case when s is equal to minus dij. But the point is that with probability at least half, the yj entry survives. And in fact, in practice, if D has more non-zero entries, you can, probably analyze this to say that, even more of the Ys are likely to survive. But the point is that the Yj entry here is non-zero with probability at least half. And, you just want a non-zero vector. You want at least one of the Yj's to survive and be non-zero. So if one of them survives with probability at least half, then basically you can conclude that your y is non-zero with probability at least half. So essentially, we are in business. We are in business because what we have managed to show is that this vector y is like all the yj's are 0. That happens with probability at most half. And I don't know if the analysis can be tightened, but my guess is that in practice, it's going to be quite a bit less than half, I think. But don't quote me on that because I'm not quantifying that in any way at the moment. One thing that you can do, however, if you're not comfortable with probability half, because that sounds like a monkey trick then, because, you give a false positive with probability, chances are that you give a false positive with probability half. And if that's uncomfortable, then you can repeat this algorithm a few times. And then what are the odds that your matrix wizard was cheating, but somehow you end up being unlucky every single time? This is a standard technique called boosting, where you just repeat your experiment to increase your confidence in the outcome. So in the miniature, it suggested that you repeat this 50 times, which is not a big overhead. So considering the algorithm is by itself really efficient, right? Because you're only computing the action of 3 matrices on an n-length vector. So that's something that you can afford to repeat a constant number of times. And by the time you've done it 50 times, your probability of giving out a false positive is basically negligible. So if you repeat your experiment 50 times and each time the outcome is a thumbs up, then you can be increasingly confident that you have said the right thing, that the matrix wizard was actually doing its job correctly. But if it wasn't, then there's a good chance that in one of these iterations, you will actually catch hold of it. Okay. All right, so that was basically it. Are there any questions or comments or anything that was not clear, perhaps? I'm happy to go back to anything based on reactions. Are we taking ABC to only be 0, 1 matrices? I think what I was saying earlier is that we can assume that ABC are, the entries are basically rationals. And the random vector is chosen to be a vector with entries in 0, 1, which I think is fine. We are not, the reason I mentioned that we're working with rationals is to say that when we are taking these sums, previously we have done things like work over F2 and strange things happen, or the mechanics of the computations are different. But here I think we're just working over rationals, but we're tossing a coin. So 0 and 1 are also entries in rationals, so that's fair game. I think we just toss a coin to determine the vector X. Can we use the black box to do the CX and ABX multiplications also? So, right. So the black box multiplies 2n by n matrices. I'm not sure if, yeah, well, so the point is, I mean, n squared is, I guess, something that's a reasonable baseline, because whatever this black box algorithm is, it still has to presumably, I mean, assuming that we're doing standard things, to multiply A and B, it still has to write out the output C, which is n by n matrix. So any matrix multiplication algorithm has to spend n squared units of time just writing the output, forget about, even the computational overhead. So n squared is not an unreasonable amount of time to spend to multiply two matrices. So given that you're going to spend that time anyway, the sanity check algorithm also spends not more than quadratic time, right? Because you're essentially computing the action of an n by n matrix on a vector with n coordinates. So that's another vector with n coordinates, and each of those entries take n operations to compute. So this is basically an order n squared thing being done thrice. So I think that's not unreasonable, is what I was.
I have a quibble here.
Okay.
I mean, in this particular model, if you're writing the matrix explicitly here, you have to give it an A and a B, right? Then the length of the input is n squared.
The length, right.
Yeah, so what you're really doing is a linear diagonal. Yeah,
it's
in the length of the input.
Correct. It's linear in the length of the input. That's a very valid point. So I think I kept saying quadratic time. That's quadratic in the dimension, but linear in the input. Absolutely. So so the point in response to the question in the chat was that you might as well spend this time if the hope was to speed things up by using the black box. Well, I'm not sure how to use the black box that's designed to multiply two matrices to compute things like CX. Maybe you can do that by just padding X. I mean, putting in X as one of the columns of an n by n matrix, which is zeros everywhere else or something like that. You could probably do that, yes, but I suspect that you're anyway going to hit the n squared bottleneck. So because the wizard is not going to do better than, like when I was saying linear in the size of the input, and that's what this chap is also doing. Oh, and I think a better philosophical reason for not using the black box is that that's the thing you're suspicious about, right? So you might worry that the black box is also gaming the outputs of these things. So maybe it's better for the sanity check algorithm to be a self-contained thing that you control. I hope that makes sense. We can take, yeah, right. So Joel, I think you said the same thing. Sorry, yeah, I think I just saw that in the chat. Train a neural network to multiply matrices and do a sanity check. Yeah, that should definitely be fun. Janki has this comment about the connection to cycles. Was that from the previous discussion about the triangle? Yeah, I think There's definitely some very nice things that happen when you go to higher order powers of the adjacency matrix. But like I said, we have to be kind of careful about the distinction between simple cycles and cycles that basically overlap themselves. Oh, Joel is saying use the black box to do funky things like some kind of a halting problem setup. Okay, that's currently a little above my pay grade. I'm the halting problem frankly gets me all very confused very easily, but I will digest your question offline for sure. Yeah, thanks for that suggestion. Yeah. Janki, if you do try to train a neural net, let me know. I think it'll be fun to share. Or just post on Discourse if you have a chance. Awesome. All right, that was a very fun discussion. Thanks so much, everyone. I think this being just a little over 15 minutes over the